Okay, so we just talked about moving one character from the source to the destination. What if I want to move something other than a character? Let's say it's a word or a double word. I can do that. There may be, these are going to be numeric values. So, and in this case, we're looking at copying an array of integers from a source to a destination. In this case, I'm not going to have a null terminated string. So where we had the check for the null at the top of the loop, I'm not going to have that. After I load the length of the string, I need to check it to see if it's 0 before we ever get into the loop. But then I want to also check for 0 inside the loop. We will look at this in class, but just something to think about. Okay, and again, in that case, instead of using move SB, I would be using move SW or move SD. All right, so let me talk about repeat prefixes before we get into the rest of the string instructions. The repeat prefixes actually correspond to two different single byte codes. They're not themselves instructions. These are prefixes, sort of like the size prefix when we were learning machine language encoding. These prefixes supplement the machine codes for the primitive string instructions, making new instructions. So, let me, what they're going to do is cause that primitive instruction to continue either a certain number of iterations or until some condition is satisfied. So let's look at, there are 3 of them. The first one is kind of the basic one, repeat. Repeat prefix, very similar to the unconditional jump, is going to repeat. It won't be checking anything before it starts. So for that reason, it's usually used only with move string and store string because both of those do nothing more than a move. Move doesn't affect the status bits and E flags, therefore there's no reason to check the status bits and E flags. Now, this is itself, we said this is going to generate new instructions. Let me show you the algorithm for the repeat prefix, okay? So this one's going to say something along the lines of the following. While count, well, let's assume a count is in ECX. So let's say while ECX is greater than 0, then we want to get into the following loop where we perform the primitive instruction and then we decrement ECX. And that's what we do here or end while. So in this case, that is the algorithm that the repeat prefix is going to execute. It will only perform or execute the primitive instruction if the guard is satisfied, the condition is met. Okay? If ECX or my count encounter is greater than 0, then I'm going to perform the primitive instruction, but then I'll decrement ECX afterwards. Okay? All right, we're going to do several examples with these, but one of the ones we'll do in class is we're going to modify where we copy a string of integers from source to destination to use repeat instead of our loop structure. When you start to use the repeat prefixes, you're going to notice that your code is going to become very small. Primarily because you're not going to have the loop structure, the labels, decrementing something, etc. So we'll do that one in class as well. Okay, and I'll go over those when we get to class. All right, additional repeat prefixes. We looked at repeat, but I also have repeat while equal and repeat while not equal. Repeat while equal is equivalent to repeat while 0. Not equal is equivalent to repeat while not 0. Each of these is appropriate for use with string commands that will affect the 0 flag. Use with string commands that affect the zero flag. In particular, compare string and scan string. When we're comparing, remember what a compare does. It's comparing source and destination by subtracting them. Scan string does something very similar. It's going to scan for the occurrence of a certain value. To do that, it's going to do subtraction. So again, both of these, because they're doing subtraction, will affect the status bits and E flags, zero flag in particular. Okay? All right, how do these guys work? They work very similar to the repeat prefix, where it iterates the primitive instruction while ECX is greater than 0. Okay? Each of these also examines the zero flag after the string instruction is executed. Okay? All right, repeat equal, repeat while 0, continue iterating while the zero flag, now let me just write this down. Repeat equal, repeat 0, continues iterating while the zero flag is set. Okay, as it would be following a comparison when two operands were equal. Repeat not equal and repeat not 0 are going to continue iterating while the zero flag is cleared. So one thing I wanted to tell you, they're not producing, I'm not going to draw out the same algorithm because they don't produce the true while loops with the conditions that we showed for the repeat prefix. The value in ECX is checked prior to the first iteration of the primitive instruction. However, the zero flag is not checked until after the primitive instruction is executed. So that turns out to be very convenient since the instruction is skipped for a zero count, but the programmer doesn't have to do anything special to initialize a zero flag prior to repeating the instruction. So because of how it does this and when it does it, it's very convenient for us, the programmer. All right, let's look at compare string. All right, compare string, as we mentioned before, subtracts two strings, setting the status bits and E flags as they should be, depending on the result of the comparison. Neither source nor destination are changed. They're appropriate to use. It's appropriate to use a conditional jump afterwards. If they're used in a loop, it's appropriate to follow it with a conditional jump. Any one of the conditional jumps that we've learned, and again, we'll do some examples where we look at this. And if I use repeat while equal or repeat while not equal, I can do the same thing there. I can use repeat equal, repeat 0, repeat not equal, repeat not 0 with compare string. All right, scan string. Oh, no. Let me tell you a little bit about this example code. We want to compare two strings to see if they're identical. Maybe I'm going to use this to grade a true-false portion of a test or something like that. Okay? So we'll do that one in class. Now let's go to scan string. All right, scan string is used to scan a string for the presence or absence of a particular string element. So it's scanning for a particular element that is normally in the accumulator, and it's going to be scanning the destination. Okay? So the string which is examined is a destination string. So it's in the element being examined is being pointed to by EDI. The accumulator contains the element that we are scanning for, and of course, since scanning involves subtraction, this will affect the status bits. So repeat prefixes can certainly be used. All right, more examples for class. Oh, this is fun. We're going to modify sequential search with parameters so that we find the last occurrence of a search key. Now we're going to use some of our string commands to do that. All right, finally, 2 more. Let's start with store string. Store string copies a byte word or double word from the accumulator to an element in the destination, or being pointed to by the destination index register. This affects no flags, no status bits in eFlags, so only the repeat prefix is appropriate to be used, but when repeated, it's going to copy the same value into consecutive positions in a string. So, not a problem if we want to initialize all of the values in an array to 0 or some other element. Okay? All right, one more. Well, one more of these, and I've got an additional string command I want to show you. Load string. The load string copies a string element to the accumulator, so it's going to load it from the source. The source is pointing at an element. It's going to take that source element and copy it to the accumulator. This one, it's a move, so it's going to set no flags, so I can use the repeat prefix, but it's not helpful. I can do it. As I mentioned at the beginning, we're going to see this when we want to get an element, process it, and store it. So load, process, and then store. And I've got an example. This last slide is a new instruction I'm going to show you that does translation. XLAT is an instruction that translates one character to another. So prior to translation, the character to be translated is in the AL register. The instruction works by using a translation table in the data segment to look up the translation of the byte in the accumulator. The translation table normally contains 256 bytes of data, one for each possible 8-bit value that could be in AL. XLAT, the instruction, has no operands, but assumes the character to be translated is in AL, and it points to the translation table in EBX. Okay? All right, guys, that's it for Chapter 8. We've got a lot of examples to do in class, and I'll post Chapter 9 shortly.